Students, I welcome you in today's session of physics. And in physics, I am going to take your chapter number 21, which is known as diffraction of light. You can see here, this is the chapter of diffraction of light. Now first we discuss what we have to study in the syllabus. This is your syllabus. So in this chapter, you have to study about the Fraunhofer diffraction due to a single slit width of the central maximum. Clear? So let's start it. Come to this first one, which is the diffraction of light. So what is the diffraction of light? Diffraction of light is nothing but the bending of a light through an obstacle is called diffraction. Clear? So you can see here, in an opaque obstacle or aperture be placed between the source of light and a screen. Suppose if you put a aperture or any obstacle in between a source through which a light is coming out and a screen, so a sufficiently distinct shadow or an illuminated region is obtained on the screen. So what you get there? You will get there a region on the screen which is illuminated. So this shows that the light travels approximately in a straight line. So it shows the path of the light ray. Now if however the size of the obstacle or aperture is small, comparable to the wavelength of light, then what happens? There is a departure from the straight line. Means if the aperture of the obstacle is very small, then what happens? There is a departure from the straight line. So the propagation of light bends round the corners of the obstacle or aperture and enter the geometrical shadow. So the bending of light round the corner of the obstacle or aperture is called the diffraction. That is the thing I told you. What is the diffraction? So it is a characteristic of wave motion. This all thing we study under the wave unit or wave motion. Here you can see, this is the figure given here. And what is the figure showing on? The diffraction of light wave at a small aperture is shown here in the figure. So a plane wavefront is advancing toward the small aperture in a cardboard. Now most of the parts of the wavefront is reflected back from the cardboard and only a small portion in the middle is passes through the aperture. Clear? So as the middle portion of the wavefront reaches the aperture according to the Huygens principle, the aperture acts as a new wave source. Clear? So hence a spherical wavefront, you can see here, this is the spherical wavefront and this is the plane wavefront, emerges from the aperture and advances with the same speed as the speed of the plane wavefront approaching the aperture. So we know that in a homogeneous medium, the wavefront is always perpendicular to the direction of the propagation of wave. So hence, as shown in the figure, the waves emerging from the aperture move not only in a straight line but also bends. So this is the diffraction of wave. Clear? Now if a screen is placed behind the aperture, then the intensity of the light emerging from the aperture is disturbed upon the screen in a certain manner depending upon the nature of the aperture. So the intensity of the distribution upon the screen is called the diffraction pattern. Here you will get the diffraction pattern. When a light is passed through a slit, you can see here, this is called the slit, the small aperture, you can say it, or you can also call it as a slit. Clear? Fine. So now we will move to what is the Fraunhofer diffraction to a single slit. This is the most important one because there are the two kinds of diffraction as I told you before starting the chapter, Fraunhofer and Fresnel diffraction. So what is happening in the Fraunhofer diffraction? I tell you in a brief. This is the, you can see here, this is the experiment or the Fraunhofer diffraction. So in Fraunhofer diffraction, a central bright band, what happened? Fraunhofer diffraction to a single slit. I know you know what is slit. If take a cardboard and mark a sharp, take a blade and mark a over the cardboard. So you slit is the formation of slit. Clear? So to see the Fraunhofer diffraction due to a single slit, we scratch a line slit means by a razor blade on the biology slide painted black on one side. So we saw through this slit the vertical filament of the lighted lamp placed at a distance of few meters. You can see here, this is the Fraunhofer diffraction experiment. So we observe a central bright band having on both the narrows alternately dark and bright bands of decreasing intensity. So this is called the diffraction pattern. Clear? Finer the slit, broader is the diffraction. This is the important property. As the finer the slit, the broader the diffraction pattern, and wider is the central band. So if light travels strictly in a straight line, then the image of the slit would have been a fine bright line. The formation of the diffraction pattern indicates that when the light passes through the slit, it bends at the edges of the slit. Clear? So it is due to the diffraction of the light that the images of stars in a telescope do not appear as sharp point but appears as a diffuse spots. Now what happens if we wrap a colored cellophane paper on the lamp? Then the diffraction pattern is also the same color. Means it is seen that the diffraction pattern formed by the red cellophane or red light spread more than the diffraction pattern formed by the blue light. It is due to the wavelength. Fine. So from this it is concluded that the wavelength of red light is longer than the wavelength of the blue light. Here you can see the figure number 3. This is showing the diffraction pattern. You can see here the alternately dark and bright bands. Clear? So if we make the slit slightly wider, then what happened? The extension of the diffraction pattern become less and the central band also become thinner. Clear? So this is the main property. The slit, the thinner you make the slit, the broader is the band you get, and the wider is the slit you made, the thinner is the central band. So if we go on increasing the width of the slit, then after a certain limit a thin line appears, that is the propagation of light becomes approximately rectilinear, that is diffraction nearly vanishes. So from this we concluded that the occurrence of diffraction depends upon the width of the slits. So if the width of the slit is of the order of wavelength of light, then only the diffraction is strong. Clear? So diffraction of light verifies the wave character of light. This is the important one. This is written here. Diffraction of light verifies the wave character of light. Clear? Now here you can see there is a geometrical arrangement given here. This is the figure number 4, and you can see easily from this figure what is going on here. The geometrical arrangement to observe the diffraction of light by a narrow slit is shown in the figure number 4. So a parallel beam of monochromatic light, I hope you know what is monochromatic light, light of single color, whose wavelength is lambda, is incident normally upon a narrow slit. This is your slit, which is AB, and the width of the slit is how much? You can see here we take the width is small e. So is placed perpendicular to the plane of the page. So the diffracted light focused by a convex lens, which is L here, on a screen, this is your screen, placed in the focal plane of the lens. So the diffraction pattern as described above is obtained on the screen. Clear? Now this is the explanation given. I am skipping this. Kindly read by yourself, and if you have any doubt, ask me in the comment section. I am moving here. From here I will explain you. From the figure, BK is equals to AB sin theta, or you can write it E sin theta. You can see from the above figure, this one. The BK is the path difference. Clear? So BK is equals to how much? AB sin theta sin theta. Therefore the position of the first minimum, that is the first dark fringe on the screen, is given by this E sin theta is equals to lambda. The addition minima are formed at the position given by E sin theta is equals to plus minus m lambda. This is the condition of minima, where m has an integral value 1, 2, 3 except 0, because if m0 correspond to the principal maximum, and the plus minus sign here signifies that the minima dark fringes are formed on both the sides of the principal maximum, where the intensity is 0. Clear? This is the principal maximum position here, this one. Here we get the maximum intensity. I hope you understand it. Now obviously some light reaches between the consecutive minima where the weak maxima are formed. These are the points on the screen corresponding to which the path difference between the secondary wavelets originate from point A and B of the slits. So you can write here slit AB is equals to 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, and so on. So these are called the subsidiary maxima or secondary maxima, and their intensity fall off rapidly as one move away on the either sides from the principal maximum. So in general, the condition for the formation of mth subsidiary maximum or secondary maximum, this is the condition where you can write E sin theta is equals to 2m plus 1 lambda by 2 this one. Clear? And in place of m you can use the value 1, 2, 3. So the angular position, that is theta, of the principal maximum and successive minimum are given by sin theta is equal to 0, lambda by e, 2 lambda by e, 3 lambda by e. Now theta is small, so we can write sin theta is equal to c theta. Thus the direction of the various minima are given by this formula. Clear? This here you can see the intensity distribution given here from this figure. So the angular position or the direction of subsidiary or maxima are roughly given by this formula. The intensity distribution of the diffraction pattern on a single narrow slit of the width with the angle theta is shown in the figure 5. This is the intensity distribution. Clear? Now we talk about what is the angular width of central maximum. Clear? So let's discuss about the angular width of central maximum. This is the topic. Now the angular width of the central or the principal maximum is the angular position between the first minima on the two sides of the central maximum. Clear? This is the you can see from the figure, this is the principal maximum or central maximum, and their either sides are their central minimum, subsidiary maximum or minimum. Fine. Now you can see from this formula sin theta is equals to lambda by e, which is in radian, and you find out the value theta equals to sin inverse lambda by e. So its angular width is how much? 2 theta equals to 2 sin inverse lambda by e. Now what happens if the slit made narrower? This is the question. So the first minima on either sides of the central maximum occurs in the direction theta, which is given by e sin theta is equals to plus minus lambda. When the slit is narrower, that is e is reduced, so the angle theta is increased, which means that the central maximum become wider. So when the slit width is small, as wavelength is equals to lambda, the first minimum occurs at theta equals to how much? 90 degree, which means that the central maximum fills the whole space. Now there are some few important points. The diffraction is exhibited both by light and sound wave. Clear? Means diffraction occurs in both light and sound waves. The second one, transverse and longitudinal waves both show diffraction. The third one, it does not verify the nature of light, whether it is transverse or longitudinal. Now come to the fourth one, diffraction takes place when diffracting obstacle is of the order of wave. Clear? Now white light diffraction pattern, this one. So if the slit is illuminated by white light, then the diffraction pattern consists of central white maximum with few color bands on either sides. Clear? Now this is the important difference between the interference and diffraction. So following are the main points of difference between the interference and diffraction. This is important one, so kindly read it. It might be asked in your examination, what is the difference? So you know very well, interference is due to the superposition of light wave coming from two coherent sources, while diffraction is due to the interference of secondary wavelets coming from different points of same wavefront. Second one, interference fringes may or may not be of same width, while diffraction fringes are never of the same width. In interference pattern, all the bright fringes are of same intensity. In diffraction pattern, intensity of the successive bright fringes goes on decreasing. Now fourth and the last one, in interference pattern, the intensity at minima is usually 0 at very small, and there is a good contrast between the bright and dark fringes. Whereas in diffraction pattern, the intensity of minima is never 0 and there is a poor contrast between the bright and dark fringes, so that you can not able to identify the bright and dark fringes easily. So this is the end of the chapter, students. I hope I covered out all the things of this chapter, and there is nothing remaining here. So do study. We will meet in our next lecture with a new chapter. Till that, do study. Thank you, class. Thank you very much.